and the quantity of these rhomboids, but the size also, is really a good indication that the water column was almost completely anoxic up to the top. Okay, that's why people were saying, "Wow, this was really anoxic," and especially right after. This swing is also really impressive. Well, this one, I don't want to go into detail, but there is some other kind of measuring anoxic condition. And here this is ratio between some kind of rare earth elements, but also cerium, lanthanum, and so on. And showing also that we have anoxic condition into the early Triassic. But I don't go into details on that one. And so, in fact, we have plenty of criteria in order to more or less recognize full anoxic condition on the seafloor. And this is quite important to do that, especially if you want to recognize black shell and if you want to evaluate the intensity of this anoxic condition. So, for example, here, well, organic carbon enrichment, it's easy to understand. Because clearly if you have no more oxygen on the seafloor due to the fact that the bacteria did the job, well, you have a better preservation of the organic carbon. So you get more organic carbon and a better preservation also. We will talk after tomorrow about the preservation of organic carbon. And okay, you can calculate also some ratio between pyrite and organic carbon. I ratio are indicative of oxenic condition. That's to say you form pyrite directly close to the surface because the surface water were almost anoxic. This may happen actually from time to time in the Black Sea, for example. You can use the degree of pyritization of the iron. You can use pyrite rhomboid size distribution. Small population, less than 6 micrometers, are really found in oxenic waters. You can, well, the biggest one, if you have rhomboids which are more than 20, 30 micrometers in size, it means that this pyrite has been formed directly into the sediments and has nothing to do with the anoxic condition in the water column, but has something to do into the sediments. And don't forget, there is an important thing. When you bury the sediment, well, the surface, if the ocean is oxygenated, will be oxic. But since you bury the sediments, after 1 meter, the bacteria are doing the job and all is reduced. So you can create also big rhomboids of pyrite in the sediments. It doesn't mean that the environment was anoxic. It means that the sediments was anoxic, which is quite different. For example, I had the occasion to work on some boats, oceanographic boat, to take some drill core for North Atlantic. We did this for 3 months. This is this kind of ODP, RODP cruise, where scientists are invited on a big boat and you drill some cores, and directly on the boat for 3 months, you take samples, make the first observation, and so on, so on, so on. And here, this is quite interesting that when you take away a core, here's generally gray to black. And since you put it more or less in the ship, to the more or less outside, the color change, you have really to take picture very quickly because you have a color change which will occur more or less in 2 or 3 hours from this gray dark to a gray white. It means that you have the oxidation of the small pyrite that you have inside. So it means that below 1 meter, every sediment is under, let's say, anoxic condition. But I'm not talking about that. I'm talking about more or less the anoxic condition on the water column. And here the rhomboids are very useful to recognize this kind of environment. As I said, some ratio, for example, thorium, uranium, but the presence of vanadium, the presence of molybdenum is also a good indication of anoxic condition. And fine lamination, we'll discuss this also probably tomorrow. This is, or after tomorrow. Preservation of lamination, just say what? That there was no perturbation, no life on the seafloor. So, mainly anoxic condition. Especially if you have all the other parameters working together. Trace fossils are quite interesting. We'll see this tomorrow or after tomorrow. Trace fossils can be used as an indicator of the degree of oxygenation of the seafloor, because you have more or less big bioturbation, very deep bioturbation, where you have oxic condition, because, well, the sediment is very, very quickly very anoxic, but still inside you can dig quite well, quite deep. But here's that when the degree of anoxy is increasing, the animals are just remaining at the surface of the seafloor. They don't go in, and because it's a place where more or less a little bit of oxygen is left. So you have a variation of the kind of ichnofacius. You know what is an ichnofacius? The ichnofacius, this is a paleontological science which is more or less you study more or less all the trace fossils. Ichno means hidden facius, because in fact you never know the animals who did it, but well, you see his traces. It's like more or less dino tracks, for example, and sometimes more or less so paleontology is a bit strange. People are more or less spending a life working on tracks but don't know which animals did it sometimes. This is a little bit strange to me, psychologically speaking. But anyway, so banthos also, different banthos are living with different kind of intensity of anoxia. In order to support this super anoxic condition, just think about the whole Panthalassa Ocean, all over, almost all around this Pangaea supercontinent were super anoxic. And we have a proof of that because in Japan, this is a Minotamba section, Japan was located almost in the middle of this huge Panthalassa Ocean, which more or less corresponds to the Pacific, if you want, actually. And this is a very, very monotonous course here, which is made mainly of chert and radiolarian, okay? But there is two exceptions, and one of these exceptions, here's the appearance here of black organic-rich claystone, which are euxinic. In the middle of a big ocean at almost, let's say, 200,000 meters deep, you get really exactly the same Permian-Triassic boundary expressed by some black shell deposition in the middle of the ocean. That's why a lot of people were talking about a super anoxic event during this time, which may explain this super extinction that I am talking about. So perhaps anoxic conditions were characterizing, therefore, all the ocean, Panthalassa Ocean, for maybe more than 10 million years. You may understand why reef, for example, were not very inclined to reappear in such a condition. Okay, so this super anoxic event, here this gray band show more or less an ocean here at the Permian Triassic, which was quite fully anoxic, and this is only here after a few million years into the Triassic that you get more or less and less anoxic condition. And you see that only the place in between, more or less small basin between the continent, were characterized by dysoxic zones where probably animals were trying to look for shelter during this very stressed period of the Earth time. Just think, completely anoxic, we have seen yesterday that we had a snowball in the Precambrian, and here, this is probably the last time where we have also almost fully anoxic conditions to the ocean. Why? Because, well, if you cover all the ocean by ice, clearly there is no more oxygen interchange between the atmosphere and the hydrosphere, and you create some anoxic condition below the ice. So this was probably the last time where a big part of the ocean were completely anoxic. And this is proved during the snowball because we have the beef, the banded iron formation, which show almost also very low oxygen condition during this time. And so this may explain why these episodes of the Permian Triassic was so detrimental for life. And here, I like these things. I don't believe it. I will tell you straight away. But I think it's a nice cartoon, a nice example of maybe a little bit exaggerated scenario for the Permian Triassic. I think it's a good example, but I'm not sure that we can really prove it. But it's a way to explain why you have, and I think it's a nice attempt anyway, but it's remained an hypothesis for sure. This is a paper, what's the name of this guy? Yeah, Peter Ward, published in the Scientific American. And Peter Ward is a specialist of very provocative idea. He likes to be provocative. I think, you know, it's very important in science to be provocative, to provoke controversy. Agreement in science is really a bad thing, really bad. Because if every people is agreeing on any kind of hypothesis, there is no discussion, there is no science, there is no investigation. And the good idea, the discovery, generally rise from a controversy, never rise for an agreement. And I think by now in the scientific world, maybe we have a little bit too much politically correct. So maybe we don't really criticize more or less the work of the other ones. And I think from the critics, you learned a lot. It's very important to be criticized, and to be critic in front of your own work, but also on the other works. Because if everybody agree, I don't know nothing which has been important discovered by an agreement between scientists. It's always a fact that there is a discussion, and sometimes very strong discussion, as you will see for the KT boundary debate, which is still not closed by far. Here there is not so much debate because everybody agree that about this scenario. But this one is not this one, it's a global scenario. This one is a little bit exaggerated, I think. You can see here, Peter Ward was thinking that you have so much anoxia, and he made an observation here, in Namibia. And Namibia, so this is the Western Africa part, he saw some hydrogen sulfide eruption. Eruption is a little bit exaggerated, but production, let's say. But you can see on this very nice satellite image, this thing is not working anymore again. He saw this eruption here that you have here and adapt this model for the Permian Triassic boundary, because this place here, you know, in all the western part of the coast, you have a lot of upwelling activity. You go to California, it's the same. You go to Peru, it's the same. And you go to Namibia, it's the same. You have a lot of upwelling, which create a lot of nutrient, a lot of production, and you rise an oxygen minimum zone. And this is a place where anoxic conditions are prevailing. And in fact, you have a huge production of H2S, upwelling of H2S to the surface due to this anoxic condition, and creating some eruption. And I think this is nearly impossible, but it's a nice paper anyway. And this eruption will destroy more or less the ozone layer. And by this way, you increase the cosmic radiation, the UV radiation, and you destroy, not like that, it's really exaggerated, but you destroy the vegetation and the terrestrial continent. So I think it's a nice way, I would say, to link what you see in the sea, anoxic condition, leading to really this kind of huge production of hydrogen sulfide, which go, and this is due to the green and purple sulfur bacteria, which will create this upwelling and after this eruption and destroy more or less the ozone layer. It's nice, but I think it's a bit exaggerated. But it has a merit to link what you can see on sea and what you can see on Earth, on the continent. And here, this is just some kind of modeling that they did. But you know, model, you can do what you want with a model. It depends on the data that you put into a model. And actually, a lot of people are doing modeling, and they are just forgetting the data. And sometimes I think it's very, very problematic. Models is a tool. It is not really something else than a tool. It's very interesting to do modeling, but it depends a lot of the data, and it depends a lot of your interpretation also. But here, this is just this slow poisoning that is shown with the concentration of toxic hydrogen sulfide and gradual oxygen depression in the surface water. And you can see that you have more or less this dissolved hydrogen sulfide, which is increasing, especially in this part of the Tethys, Paleotethys, which is quite interesting because you will see that it corresponds to a huge migration, for example, of fish toward higher latitude, where probably the concentration of hydrogen sulfide were less. So there is probably in any of this kind of, let's say, exaggerated idea, there is always something true which can be as a message, you know. So I will not throw this paper completely to the trash, but you have to be a little bit prudent about what you are reading from time to time. Okay. Now, in terms of climate, because climate conditions were really changing during the Permian-Triassic condition. And here, this is a curve where you can see the average global temperature. And, well, you can see something which is quite clear, and you will see it's probably a lot more to the Triassic. But the Carboniferous Upper Carboniferous was very cool, glaciation. The lower Permian was cool, and after more warm, and a maximum of warming into the lower Triassic. And here I can tell you that the last data that I will show you show that the lower Triassic was really, really hot. But we will talk about that later. So we start, and this is an important point, from Carboniferous, it's an ice house, to a very hot house here. And we have a lot of proof for that. And we use, I use, for example, these maps from Scotties that you can find on the website. They are free. Scotties, if you go to ResearchGate, for example, I encourage you to go to ResearchGate. There is a huge number of papers that you can upload. And the good thing is that there is some papers that you can ask to the author, and I am answering a lot on ResearchGate because you know that this paper sometimes Elsevier is asking a lot of money for in order to get this paper, and sometimes the library cannot pay for that, the permission to upload the paper. So don't hesitate, go to ResearchGate. A lot of people are putting privately, so it's not on the side. You have to ask by email. Please, can I have this paper? And generally, if I am putting my paper on ResearchGate, it's just because I want the paper to be read. So I will send you an email with an attached file, a PDF, and this is at no cost. And you have the right to do that. You don't have the right to put it on the web like that, but privately, you have the right. So don't hesitate, go to ResearchGate, and if you need a paper, just ask to the author, because normally they send it with no problem. Okay? because the politics of Elsevier is really exaggerated. They ask a lot of money. They are doing billions with science, and we are working for them, writing papers, never paid. You never get any money to publish any paper, not in Science, not in Nature, nothing. And moreover, you have to review this paper, and you never get any money to review this paper. So I think these companies like Wiley or Elsevier or Springer are really a mafia. And I just hope that it will change. But by now, you know what they are doing. They're doing open access. Wow, nice. Open access means open. Everybody can take it, everybody can upload that. Yes, but you have to pay for that. The authors, if they want an open access in a paper, they have to pay a lot. For example, now a paper in geology, which is a very good review from the Geological Society of America, you have to pay $2,000 in order to have a 3 pages publication. Well, generally you have several authors, so it's not so expensive, I have to say. But, well, this is clearly an obstacle for publication, especially in the land where there is less money. Yes, in Switzerland, well, my university will pay. It's not a problem because it's good for the ranking, you know. So they know that, well, if it's good for the ranking, they will pay for this open access. But the problem is that I think it's not democratic at all. But there is also this Web of Science, which is really good. I don't know if you know that. This is totally illegal. And this has been done by a Polish girl, scientist, which were really furious against the politics of this big company. And here you can upload what you want. But it's at your own risk because, well, it's completely illegal. ResearchGate is legal. It's not a problem. But the other ones, be careful. You can have some problems and some troubles if you do that. Okay, so now if I just go on with about this climatic. These maps, for example, are available on ResearchGate. And you can really find it. You go to the Scotties, which is the author, Scotties page, and you can find it. And this map is quite interesting. We start in the early Permian, and you can see here that I will go there. I think it's better for you have an early Permian. They use. I will go back to the legend. I think it's important because. Okay. Yeah. Okay. This is quite important because you see the legend. In fact, during you can infer climatic condition by using some parameters, like you can see in the sediments. If I start with the cold, if you have the presence of dropstone, you know what it is by now. It's typically glacial. Tillite, which are moraine, which are the sediments left by the glacial. Glandonite, these are very special minerals which are growing in cold water, calcite mineral mainly. And this all, if you find this in a sediment, this is cold climate, okay? If you find evaporite, as I said, calcrete, which are more or less some kind of calcareous crust that you can find in arid country. Evaporite, this is arid condition, okay? Warm and arid. Tropical condition, this is generally a lot of rain. Generally, you can form coal because there is a lot of vegetation. Bauxite, which is a pure aluminium minerals almost, which means that it's formed only under equatorial tropical condition where you have rain during all year, more than in India, for example. And you can have laterite, which you can find sometimes from time to time in India. But in India, this is not on that. You can have a very special type of soils, or paleosoils, the vertisol, that you probably know, which are very rich in smectite, swelling clays, which are typical for highly seasonal climate, like the monsoon. And a lot of soil in India are made of smectite. All the paleosols which you can find around the Deccan generally are made of smectite. And smectite is a swelling, more or less swelling clays, meaning that during rain you increase the size of smectite, and during arid conditions it will shrink, which is not very good for agriculture because you will this would destroy your soils and the property of the soils. But anyway, it looks, if you have a lot of earthy soil, it means that you have a monsoonal regime, like you have in India, quite a long, let's say, arid season and short but strong rainy season. And coal-entilite, it's a cool temperate. And you can also use the clays as a smectite, seasonal, or kaolinite, very humid and warm condition. And you can also use the paleontology. If you find palms, mangrove, and crocodile on the, let's say, Antarctica, it means that, well, they did it but because it was warm, okay? So we can use all this map. And this map, well, paleogeographical map, very instructive, because for Permian, you can see that in the early Permian, this was cold. All the little cross are moraine, glacial sediments. You have some coal, but it's called cool temperate. This is typical for the climate that you have, for example, in Siberia or to the north, to the North Pole. But you jump directly to an arid belt here, which is marked by the presence of evaporite, and very, very small tropical region, which increase due to the presence of the Tethys here when you have the what correspond to China actually. So there was some place where conditions were tropical. But if you move on time and you go up to the middle late Permian, you can see here something which is very, very spectacular. This is the increase of this arid belt, the disappearance of the tropical belt on the continent. This is all arid and desertic, this Permian. And remember that, for example, you may have seen this in a lot of pictures, this Permian sandstone, Aeolian sandstone that you find in North America. It's a huge, huge accumulation of very nice fossil sand dunes, which has been fossilized completely. And these are due to wind. This is desert, okay? And this is from Permian in age, all this sphere. So you have warm temperate, cool temperate, no more ice, no more moraine. This is typically more and more warm, but also more and more arid. And what is the consequence of that? This is the global installation of a lot of evaporites basin, especially in the internal part of the continent. You get a lot of evaporite. And for example, in Poland here, you get, or in Russia, some kind of 2 kilometers thick of evaporite accumulation during this time. And I think this is very important because below this evaporite, in Siberia, you have also some coal. And, well, this is where you have the maximum of eruption. So it means that the magma will cross this coal and this evaporite. What do you have in coal? The main element that you find in coal is carbon. And in evaporite, sulfur. So CO2 and SO2. And all these things will go into the atmosphere. And this is a starting point of the explanation of this huge mass extinction. So evaporite everywhere. But there is another consequences. Remember at the beginning, I was explaining that, in, let's say, the upper part of the Permian, but not close to extinction, we have a first extinction where the echinoderms were suffering a lot. And I told you that the echinoderms were very sensitive to change in salinity. And this is clearly a huge change in salinity, because what happens, you will more or less have a sequestration of the salt in this internal basin, and the global ocean here, and especially here, will be less salty. You have a huge variation in salinity. And some animals, like the echinoderms, don't like it. So they will really suffer a lot. So these things has also some importance. If we go up with this climatic reconstruction, what we get here, and this is the early Triassic, wow, it becomes really strong. You can see here that you have warm, temperate, sometimes arid condition with calcrete up to the very high latitude, and arid condition, and the tropical zone is almost disappearing, restricted to this Paleotethys. So it means that, well, this was not a very nice time to survive, and that's why a lot of animals, as you will see, migrate from the central part down and up here in order to escape to this very bad condition. Okay, so now what was we have to look for the killer, if you want, the main trigger. And here I will present you the main killer during these things. This is a flood basalt, and it's a massive volcanism. These are the Siberian traps. Siberian traps are really huge in terms of superficie, probably equal to the Deccan in terms of volumes, a little bit less, I guess. But there is a huge difference, as you will see, in terms of efficiency. But the thickness is a little bit the same. Deccan is around 4 kilometers in total. Here, I would say it's almost 4 kilometers. More the volumes of flows is a little bit less also, but it's not very well known. Deccan is a lot better known because Siberia is not an easy way to go. You have to take an helicopter first of the Russian army. Well, if you want to come to see it, just take an helicopter of the Russian army. They are very dangerous guys. They are generally completely drunk when they arrive in such country. So it's not very, let's say, safe. And you arrive along this river, and you have to take some small boats. And after, okay, you have to climb, and this is full of mosquitoes because you go there during summer. It's not a very nice place to do geology because, well, there is no road, nothing. And there is almost no red ball, which is not very good for the dating, as you will see tomorrow of the Kitty boundary. But anyway, some crazy people, especially from Norway, did it. And what they found also is quite interesting. First, well, there is a big difference with part of the Deccan, because maybe the story of the Deccan is changing by now, because we have some new findings that may explain a little bit the same in part, but for sure that the Unpermian had a lot of gas venting, and in fact this magma chamber was going through pipes, dikes, and so on into two kinds of sediments, as I said, evaporites and coals. And so this is clearly very, very, very lethal for the biosphere, because you will charge more or less the atmosphere with a lot of CO2 and a lot of sulfur dioxide. Just a map showing you where are the Siberian traps. I need, sorry, they are here. You probably know. The Siberian traps are here. Just for comparison, you have here the Deccan, and some other ones which are quite big, is the Columbia River, the North Atlantic volcanic margin, and Parana-Intendeca. All this volcanism is continental. That's why there was so efficient for the mass extinction. But you can also see that there is some submarine plateau, like the Ontong Java here and here, like the Kerguelen, which are huge, bigger, but they were submarine. And that's why probably they were not so efficient, enough efficient to create a mass extinction event. There was also some massive explosion. Explosive volcanism is well known because we have zircons, bentonite in a lot of places, for example, in China. And these pyroclastic events could lead to, in this general warming curve, to some short cooling event. And this also can add some really lethal condition for the biosphere. Okay, now, just to abstract, to sum up a little bit what we have seen till now. Okay, what we have seen, here's a first pulse of extinction, predating a few million years. This is a Guadalupian end mass extinction and Guadalupian mass extinction, which is marked by a huge extinction of echinoderms linked to the change in salinity of the ocean. But you know that there's another group. And here, Courtillot people from France make the correlation of that event with the emission traps. Maybe, maybe not, I don't know. This is not very sure, but we have some evidence, more evidence that the Siberian traps were really coinciding with the massive extinction of the Permian Triassic, where you have the maximum of extinction corresponding to this minimum in delta C13. And this minimum, to me at least, is probably linked to the Siberian traps activity, which coincide very, very nicely with this huge mass extinction event. So again, you have a nice correlation between this. I already show that. Again, you have a very nice correlation between the age of the continental flood basalt oceanic plateau and the age of the mass extinction event. And you can recognize maybe the end Devonian. Surely here the Guadalupian and mass extinction. The end and the end Permian, here, the second point. The end Triassic, we'll see this tomorrow very quickly, and the end Cretaceous. So again, there is a very nice correlation here. And now we can start to think a little bit about the mechanism of mass extinction and to talk about this Orient Express crime. I will finish this presentation of today very quickly. So this is the extinction mechanism for the Permian Triassic. And here, in fact, this is sum up, is taking in account all the geochemical, paleontological, climatic, and so on indication that I just show you for this huge mass extinction. So it's a model including global warming and anoxic for this mass extinction. Okay, and interestingly, you can use it for the marine mass extinction and the terrestrial mass extinction. So I will start with the marine, so it will be more easy here. Maybe this thing is working. Okay, so here what we have is the following. Okay, we start from the Siberian trap eruption. You get the CO2 emission, and this is explained by the negative delta C13 excursion that I show you, okay? And after, if, you have also the thermogenic gas emission, which is explained, again, this negative excursion. And if you increase the CO2 emission, you get the warming, global warming, greenhouse effect, okay? And this global warming of the ocean may also dissociate the clatrate, the gas hydrate, the methane hydrate, which may again amplify this negative excursion. But these things, as I will explain for the PTM, it's quite important because this will create more CO2 into the atmosphere. Because, well, these gas hydrate, which are stocked on the slope at 2 kilometers depth into the ocean, will melt, and the methane will be oxidized into CO2. And when you do that, you create an oxy also, because we are using the oxygen of the water column in order to get this CO2. And the CO2 will go into the atmosphere and participate to the general warming. On the other side, this global warming will lead to a stratification of the ocean and to, acidification and oceanic anoxia. And this will lead to the extinction of the marine fauna. Now, I just moved to the continent. This is a good side. And here, the Siberian trap emission will mainly, clearly still also CO2 has something to do, but you have some sulfur dioxide emission and some also lethal gas, which are more or less including chlorine, fluor, and nitrogen, and things like that. And all these things will participate to first SO2 emission due to the nucleation of that with the particles to volcanic darkness and short episode of cooling, which may more or less explain on land the shutdown of the photosynthesis. And this shutdown could be accelerated by acid rain. And also this kind of emission may also destroy partly the ozone level and increase the UV radiation. And all these things may create more or less the terrestrial mass extinction, especially for the plants, okay? So I think it's a quite convincing explanation. And here, well, I put that one. This is in French, but doesn't really matter. You know, we are calling this mover of mass extinction because, in fact, this is an addition, as I put here. This is more or less French. It's very similar to the English here. In fact, you have, more or less volcanism here. The change for the ice house to hot house, regression, change in salinity here, increasing cosmic radiation. This will create a threshold where you have already extinction before really the massive extinction, but the transgression and anoxic condition will create a hyper extinction. Orient Express Crime now. The story is very simple. I don't know if you know that book. Well, Agatha Christie, it's an old English lady. I think she died 20 years ago. Maybe you don't know these books, but these are more or less thrillers books where you have a detective. Maybe you know this name, Hercule Poirot. And Hercule Poirot, this policeman, is in a train. And, he found a dead guy. And this guy apparently has been killed by 12 stab of knife like that. And clearly, well, a very bad guy. This is for the English morality. And Hercule Poirot is looking for all the books to one guy, one killer, one responsible. And in fact, at the end of the book, you learned that 12 people have been killed, were killing this guy. Each of them just giving a knife stab to this guy. And this is almost the same thing here. In fact, there is different triggers here that were acting in the same time. and they were responsible. Okay, so that's why this comparison with the Orient Express crime. This is not a single cause, and life on Earth is very complex, and you cannot explain even the dinosaur decline and extinction by one single cause. This is a conjunction, more or less several causes acting up at the beginning gradually. You get more and more stress in biosphere, and after you cross a threshold which will lead to the extinction. This is exactly what happens here. And after in order to finish with that, we have to also to explain why the recovery was so long. And here it's again a very nice paper from there is no thing. It's from a China guy, I think it's Song, S-U-O-N-G. Song et al. With Paul Wigman. What they did here, you have the Permian-Triassic mass extinction, which is just here, okay? And you can see here, well, some curve, the number of conodonts here, which are surviving, hopefully, because we need them for biostratigraphy. You see the number of ammonite here, which are almost disappearing at the Permian-Triassic boundary, reappearing, disappearing. And here there is a period where they are almost disappearing again, both conodont and ammonites. Here's the number of radiolarian going from 50 to 16 at the PT, but not so much afterwards. Here, the disappearance of decrease in diversity of bivalve, gastropod, and brachiopods. So you can see that the recovery here, you have 251, and here you are somewhere 5 million years later for this recovery, for example. And the same can be said for algae, for amnifera, and so on. Long, very long recovery. The same can be said for the marine fish, and the same can be said for the plant, where you can see that, well, the conifers were dominant, and after you have only bryophyte, very special pioneer plants surviving. In order to get the conifer dominant again, you have to wait also a few million years. Why? And one explanation is the fact that, well, you have this huge Permian-Triassic mass extinction, but if you measure more or less the temperature of the ocean during this early Triassic, you can see that it was really warm, and there is here a record of the temperature of the SST, sea surface temperature, which was very hot in the Paleothetis, 40 grades. 40 grades, I can tell you, it's very hot. And it's why the reef didn't reappear for a long time. The reef are reappearing somewhere higher up. And this very hot ocean, hot house period, can be seen when you are looking about the distribution, for example, of fish and tetrapods during this time. You can see here that the tetrapod, for example, and the fish during the late Permian were present almost everywhere, but well, especially clearly in higher latitude, because it was already quite, let's say, hot. But you can find the fish also in the Paleothetis. And during the early Triassic, there is no equatorial tetrapods here. They just disappear. And very rare equatorial fish. They just migrate toward higher latitude. And these things, this is a paper, of Sun et al. It's from China. But very good paleontologists like Benton did exactly the same kind of statistic. And I just heard a talk from him at the last GSA in USA in September, and he obtained exactly the same kind of data. So It means that, well, the fish, for example, is here. If you look at the fish, well, during the mid-early Triassic, where you have really this very hot house, the equatorial Tethys was almost completely devoid of fish and marine reptiles too. And every tetrapod, fish and so on, return only way after to lower latitude, and life returns to the tropic only in the mid-Cretaceous. And in the mid-Cretaceous, again, you have the reef. So this mass extinction is, you cannot see the Permian-Triassic mass extinction only by looking just the boundary, where you have seen a lot of things are more or less clearly occurring, but you have to see the global image, what happens before. Permian was very arid, upper Permian, and you move from glacial to very arid condition. You don't have any more coal. And on top of that, you get the volcanism, which will accelerate the things. And after, on top of that, due to this volcanism, you have so hot temperature onto the ocean that you have all this kind of migration, which may explain why the recovery was so long. Okay? So this was the things that I want to tell you today about the Permian-Triassic, the mother of the mass extinction. And tomorrow, this is Wednesday, tomorrow. So what we will do tomorrow, I will speak a little bit about, in the morning, about anoxic events, because I think that we will talk, no, I will first speak, about the end Triassic, Jurassic mass extinction, but quite shortly. And after, we will talk about the anoxic event from the Cretaceous mainly, because I think there is a lot of things interesting here happening, and you have some of this event, not really black shell, but in India, the Cauvery Basin, Arialo Basin, for example, have the Cenomanian-Turonian boundary, where you can find the more or less sediments of the same age. In Tibet, also in China, but you have the same in Nepal. You can also find some Cenomanian-Turonian boundaries. So we'll talk a little bit afterwards about anoxic events in more details. And Thursday, I think we will spend the whole day about the KT boundary, because, well, maybe not the whole day. We will see. We'll start probably the KT boundary also tomorrow, finish Thursday, look at the PTM, and finish Friday with the Anthropocene and the discussion about all these things. Okay, thank you very much.